Okay, so electrostatics. So in electrostatics, generally we discuss two parts, part 1 and part 2. Okay, in part 1, basically we discuss, in today's lecture, we basically gonna discuss the part 1 only, that is electrostatics 1. Okay, so in this chapter, first there is a concept of charge, electric charge. So properties of electric charge is what? We know charge is conserved and charge is quantized. Conserved, quantized. Okay, and charge is transferable. Okay, it's a scalar quantity. So first it's a scalar quantity. So these are some basic features of a charged particle. That is, it's a scalar quantity. Charge is conserved. Charge is quantized means any charge is an integral multiple. Yes. Charge is conserved means charge cannot be created or destroyed. Okay. The next thing is conductors and insulators. So what is a conductor? Conductor is a metallic surface, basically, not maybe non-metallic, of course, but conductors, the main features of conductors is that electron can flow easily. Basically, it means that free electrons are available in conduction band, and conduction band and valence band overlap with each other. Now, as valence band overlap with the conduction band, free electrons are available in conduction band, and these free electrons take part in conduction. Okay. Take part in conduction. Okay. Next thing is Coulomb's law. Coulomb's law. So what is the Coulomb's law? This is basically an inverse square law. Inverse square law which describes the relations, the force acting on a charged particle due to other particle, another charged particle. So if we consider there are two charges there, one is q1 and another one is q2, and the distance between them is basically the r. Okay, q1 q2 by r square. Now, yes. Now, f is proportional to 1 by r square. This thing is called inverse square law. These things is the features of inverse square law. Okay, and this is also proportional to the product of two charges. Okay, now the difference between the gravitational force and this force is that this force can be of both type, attractive and repulsive. Whether the gravitational force is only attract, while the gravitational force is of attractive nature. Okay. Now, so this is a force, of course. So this is a vector quantity. Now, as this is a vector quantity, we have to analyze this force in vectorial diagram. Okay. So if this is the x and y coordinate, xy Cartesian coordinate, sorry, xy Cartesian coordinate, rectangular Cartesian coordinate. This is the origin, and we are choosing 2 points. One is A and another one is B, with position vector like this. If this is the position vector of A, that is RA vector, this is the position vector of B, that is the RB vector. So what should be the position vector of this line? What should be the RA minus RB? Because this is directed like this. Okay. Now if this is Q1 and this is Q2, and both Q1 is greater than 0 and Q2 is greater than 0, then the force acting due to Q1, force acting on Q1 due to Q2, I'm just writing like this, force acting on A due to B is given by K Q1 Q2 by no, we have to like this. Yes, this is modulus of R square. Up to this point is right, you are correct, but there should be another term, that is the vectorial term, the unit vector along this line, that is RA minus RB by mod RA. Okay, so this is basically K Q1 Q2 RA minus RB. These are vectors, of course. Okay, by mod of RA minus RB. So okay, so this is the vectorial expression of force, Coulombian force. Is these things. Okay, so I'm not going into more deeper section because this is the basic for your WBJEE examinations. And of course, remember, please do not forget the value of K. Okay, so K is what? K is 1 by 4 pi epsilon naught. Okay, or epsilon naught of the electrical what? Permittivity. And what is the value of epsilon naught? 8.854 into 10 to the power minus. Okay. So what should be the unit? Okay, something unit. See in the books. Okay. So unit is basically, you can calculate the unit of force by unit of, okay, no, unit of charge square by unit of force into unit of this thing, distance square. Distance, yes, distance square, of course. Please also please remember the value of K. Value of K is equals to 9 into 10 to the power 9, almost. Okay, and E equals to epsilon R epsilon naught, where epsilon R is the relative permittivity of a medium. Okay, So electric force is basically medium dependent. Okay. Okay, so electric field. So electric field is defined as the force per unit charge. Okay. So by Coulomb's law, we know that the charge Q experiences a force and it exerts an equal force on another charge if we place two charges. Let's say there is a charge Q, capital Q, and there is a charge small q. Now this charge is called test charge. Okay. Now what should be the force on this charge by this charge? So force on this charge should be like this, F, and that is equals to K Q capital Q by R square into the unit vector. Unit vector is like this. Okay, I am joining this one. Okay. Now, so what is the force per unit charge? That is F by Q. So we are dividing a vector by another scalar quantity. So we are getting another vector quantity, that is this. That is equals to KQ by R square. Okay. So electric field is basically electric field due to a point charge. This is a point charge. It's basically like this. If this is Q, and this one is small q, means this one is a point A, and we are willing to calculate the electric field intensity at this point due to this charge. So the direction should be like this. If this is the unit vector r cap denoting the direction of electric field, and if the distance of this point A is r from this q, then electric field is equals to kq by r square into the unit vector. Okay, so if we assume a region of electric field and we place an electric charge in that region, then this charge will experience a force. Okay, if there is a region with electric field with non-zero electric field, of course I'm writing electric field means it should be non-zero, with electric field, then if we place a test charge in this region, the charge will experience an electrostatic force. Okay, so field is a thing, is a quantity. By means of field, a force interact with a particle. Okay, now for this electric field, a charge interact with another charge. Okay, so every non-interacting force should have a field, not electric field. For electrostatic force, there should be a electric field. Okay, so electrostatic force interacts with the particles, means charged particle with the charged particle by means of electric field. Okay, so next we should derive the expression of electric field. Now this is the electric field due to point charges. Now if we want to calculate the electric field due to a system of charges, then the expression should be like this. Let's say this is our xy Cartesian coordinate system. Let's say there are charges q1, q2, q3, q4 dot, like this is a charge qi. There is a point G. Okay, now let's say the distance between these 2 points is, one second, distance between these 2 points is Dij. Okay, so this is a position vector, of course. Dij is the position vector. Okay, so force on J due to I sorry, we are calculating electric field. Okay, let us derive from the expression of force. Let us place a test charge here. So force on charge J due to the charge Qi is equals to Fji, and that is equals to K Q Qi by Dij mod Dij whole cube into Dij. Okay, so this is the expression of force due to this charge at Ri. Okay, so this is the position vector of this charge is Ri. Now the net force is basically F net is basically the summation of Fji. Summation will be run on I is equals to 1 to n. Let's say there are n number of charges. Okay, so in this expression you can just take common K times Q, and there will be term like Qi summation Qi by Dij. This whole thing is under the summation. Okay, 1 second, let me rewrite this thing. Qi Dij mod Dij I equals to 1 to n. Okay, so this is the F net, and what should be the value of electric field? So electric field is basically KQ by Q I equals to 1 to n. Okay, okay, fine. So this is the due to the system of charges, and this particular category is under the discrete charges. This charge distribution. Another type of charge distribution is continuous charge distribution. Continuous charge distribution. Okay. For the continuous charge distribution, let us take this is a continuous. This is a body with uniform charge distribution. Of course, we cannot calculate the electric field by mere integration for this type of body, where the distance vector, the electric field will vary with the distance, and this type of situation is very complex situation for integration. Okay, so let me take a general expression for this one. So I am taking this. Let us take an elementary charge dq, and we are willing to calculate the electric field intensity at this point A, which is at a distance of r, let's say smaller. Okay, so electric field is a function of r vector, would be like this. Now for this type of case, we are just interested in, we are specially interested in the magnitude of the electric field. Okay, so this is K integral dq by r square. Okay, so we can take common integral dq. Okay, okay, so this thing should be, q is a function of r, of course. We will see this. So this thing should be run up to 0 to q, 0. Okay, where q will be a function of r. Okay, so electric field due to point charge, we have discussed this thing. Then electric field uniformly due to uniformly charged rod. This is another important derivation. Okay, let me derive this thing. Okay, so for this one, we have to choose an elementary charge like this. Let's say at a distance x, we are choosing elementary distance dx. like this. Okay, so this is dx. Now let us consider the lambda is equals to the line charge density. We'll discuss about charge density in electrostatics 2. Lambda equals to line charge density, and this is x. So what should be this distance? What should be this distance? Let's say, and what is the relation between x and r? We are given theta 1, theta 2, and r. Now what is the relation between x and r? Let's say this angle is theta. Let's say this angle is theta. So x by r is basically what? Yes, x by r is basically tan theta. So this is basically like this. One second, please. This angle is theta. This is dx. One second. This is x, and this one is r. So we can resolve the total electric field. So electric field due to the dx means this is equivalent to the equivalent charge is equals to dq equals to lambda dx. So this is dE. Yes. So this thing is what? This thing is also theta. So this is equals to dE sin theta. Sorry, yes, dE sin theta. This is equals to dE cos theta. Okay. Now this is the perpendicular, and this is the parallel. E parallel. Okay. Okay. So let me take a space here. Okay. So first we want to calculate the perpendicular component. Let's say, so this is basically dE cos theta. And what is equals to dE? dE is basically equals to kq, and this, let's say this is the distance d, k dq by d square. Okay, into cos theta. Now k dq by d square, what is the d square actually in terms of r? In terms of r, so r by d is equals to cos theta. R equals to d cos theta. So d square equals to basically r square sec square theta into cos theta. What is dq? dq is basically lambda dx by r square, and we take this sec square theta in the numerator, then we can get the cos cube theta. Okay. Now you know that r by x equals to what? Sorry, x by r equals to what? Tan theta. So dx equals to what? R sec square theta d theta. R sec square theta d theta. Okay. So you can write here basically k lambda dx is what? R sec square theta cos cube theta d theta by r square. So this is basically k lambda by r. Sec square theta and cos square theta are cancelled out. So 1 cos theta left times d theta. Okay. So this is the DE. So now this is DE. Now E perpendicular is what? E perpendicular is basically integration of the E perpendicular. Okay. So this is basically what? K lambda by R cos theta d theta. Okay. Now we have to think about the limit of the integration. What should be the limit of integration? Let us say that we are taking this. Let me draw the picture in this here. Let us say this one is theta 2 or theta 1. Okay, this is theta 1, no problem, and this is theta 2. This is the equivalent of, like this, sorry, so this thing is equivalent of minus theta 1, like this. Okay, so we can take from minus theta 1 to plus theta 2. We can take like this, or we can take minus theta 2 plus theta 1. If we take the minus theta 1, so this represents this terminal, and if we take the plus theta 2, this will represent this terminal. Okay. Okay, so this thing we can write minus theta 1 to theta 2. So that is minus theta 1 to theta 2. So k lambda by r we can take common, because this is the function of theta only. Yes. So this is basically k lambda by r, and integration of cos theta is basically sin theta. Sin theta 1 plus sin theta 2. Okay. So this is the expression of electric field. Let us take another page, discuss the DE parallel. DE parallel is basically DE sin theta. Now, one second please. Now if you see that this one up to this point, this cos theta, 1 cos theta is due to this cos theta. Okay, so if this cos theta is replaced by sin theta, then this expression should be sec square theta cos square theta into sin theta. Is this thing clear? Any problem? This is cos theta and this is the DE. Okay, this is cos theta and this is DE. Okay, so there is a sec square theta, and if we take this sec square theta to numerator, then it will be cos square theta, and this cos theta is basically due to this cos theta. Now this cos theta is replaced by sin theta here, so our expression should be like this. From this thing we can take that our expression is k lambda by r sec square theta cos square theta sin theta d theta. Clear? So this is basically k lambda by r sin theta d theta. Clear? So E parallel is what? Integration DE parallel. So this is basically k lambda by r sin theta d theta. And what should be the limit? Sorry, this is theta 1 and theta 2. So this is minus theta 1 to minus theta 2 again. Okay. So this is basically k lambda by r. What is the integration of sin theta? That is minus cos theta. So we can just write like this, minus theta 1 k k lambda by r cos theta 1 minus cos theta 2, because cos of minus theta 1 is basically cos theta 1. Okay, clear up to this? Okay. So now if we want to find the E parallel or theta 1 equals to theta 2, then E parallel equals to what? 0. Okay, and E perpendicular or theta 1 equals to theta 2 equals to theta, E perpendicular is what? K lambda 2 k lambda by r sin theta. Okay, any doubt till now? Because 2 sin theta, if sin theta 1 equals to sin theta 2, then it should be 2 sin theta. So if we want to calculate the field at this point, so what is theta 1? That is 0. Okay, theta 1 is equals to 0 and theta 2 is also equals to 0. So E perpendicular is equals to, okay, for this case E parallel is equals to 0. Okay, now for this one, at an equatorial point, so here theta 1 equals to 0 and theta 2, actually theta 2 is not equals to 0. What is the value of theta 2 here? What should be the value of theta 2? Yes, so that should be basically 180. Okay, now for this one, E perpendicular is 0, because sin theta 1 means sin 0 plus sin 0, that is 0. And here we can write, so theta 2 is equals to 180. So if this is true, then E parallel is equals to what? 1 minus 1 minus 1. Okay. Clear up to this? Okay. Next discussion is on uniformly charged string. First case is at the center. At the center. So what should be the electric field at the center? 0. Because this is dq and this is also dq. So electric field equals to 0 here from symmetry. What should be the electric field for this one? For at a point on the axis of a ring. So let us calculate. Okay. So here we can define the lambda like this, q by 2 pi r. Okay, this one is r. Okay. Now let us consider a length ds like this. Okay. So dq is basically lambda ds. So one part is there only, that is the parallel component. Okay. Sorry, perpendicular component. Okay. dE cos alpha. Okay. Okay. So this is what? KQ by R square plus into cos alpha means what? R by root over R square. Yes, capital R by this thing. And this is what? Lambda ds. So this is basically kr by r square plus r square to the power 3 by 2 lambda, and ds, integral ds is what? 2 pi r. Okay, so this 2 pi r means q, so kq by capital R. Okay, so that part will be excluded in the video, in the recording that I will be sending. Okay, because that is a big mistake by me. This page is not. So after this uniformly charged disk, here we can consider the area charge density. Okay, D is like this. Okay, so let us take one second. dr like this. So these are some techniques for taking elementary area. Okay, so this is dr. Okay, so dE due to this dr should be what? This dr, this is basically a charged ring. What is the area of this charged ring? Not 2 pi r, 2 pi r dr. If this is dr, and this radius is, let's say, r. We like this in engineering drawing. Okay, so dE is what? Due to the charge ring. This is the charge ring with surface charge density equals to q by pi r square. Okay, so dE is basically k sigma 2 pi r dr. We are just using this expression. KQR, r means this one, means x. So KQR by capital R square. What is the capital R here? Capital R means x here, x square plus small r square, that is the radius, whole to the power 3 by 2. So this is basically k sigma 2 pi, okay, 2 pi x, there should be r dr by x square plus r square to the power 3 by 2. This is the expression of elementary. This is the expression of electric field due to the elementary charged particle. Let me write it k dash for now. Now, okay. Now let us say that x square plus r square equals to what? Z square. Okay, so 2r dr equals to just 2z dz. So here we can substitute like this, k dash z dz. Yes, so this is basically k dash dz by z square. Yes, so this is basically, ঠিক আছে, আমরা তাহলে কন্টিনিউ করি। So k dash, so this thing is basically what? R basically goes from what? From what to what? this thing is basically goes from what to what? R basically goes from 0 to capital R. So Z basically goes from x square to what? X square plus R square. Okay. dz by z square. So is equals to integration dE, it is integration k dash dz by z square. K dash z goes from 0 to x, sorry, x square, not x square. This is x, that should be x, because z square goes from x square. Okay, so that should, so this thing is basically k dash. You can do the integration and put the value here. I'm direct putting the value here. Okay, now k dash is what? 2 pi, where is the k dash? 2 pi sigma x k. Okay, this thing can be written as 2 pi, k is what? 1 by 4 pi epsilon naught x sigma. Okay, so this thing is basically, this is basically what? There should be a 2 here. Okay, okay, and x is here. So when x is there, this x is there. Okay, so this is, let's say, k double dash. K double dash is basically not x is included here. Okay, you can just do the integration. So that thing should be 2 epsilon. So E is basically sigma by 2 epsilon naught 1 minus x by r square plus x square. Okay, okay, so now we can conclude here. In the next lesson we're gonna learn about the graphs of this for these expressions, r versus e graph, e versus r graph. Okay, so you can conclude the class here. So bye.